Example 3, the curve is sine x, and I want to find the area under sine x from x is equal to pi over 6 to x is equal to pi over 2, the starting and end values. So I need to take the height of each of those rectangles, which is sine x, and times it by the width, which is delta x. And again, I want to convert this into an n expression. So I need to convert the delta x and the x into some expression of x. So to find the delta x, that's the start, we're going to, again, take this interval width from start to finish, from pi over 6 to pi over 2. So my interval width is going to be pi over 2 minus pi over 6, or 3 pi over 6 minus 1 pi over 6, which is 2 pi over 6, which we can simplify to pi over 3. So that represents my interval width. I can find my delta x by taking the interval width from start to finish and dividing it by the number of divisions, which is n. So we can make n anything. If we want to calculate a Riemann sum, we use a finite value. If we want to get the exact value and convert that into the integral, we can let n go to, we could use a limit and n goes to infinity. So my x values I have to establish. The x coordinates are going to be based on moving delta x, so plus delta x, but we have to start somewhere. So my x values are going to be starting at pi over 6, and then I'm going to add delta x, or 3 pi over n, and I'm going to do that k times. When k is 0, I'm going to be, or k is 1, I'll be at the right-hand edge of that interval. So in this case here, the rectangles I've drawn are right-hand rectangles. The other rectangles were not quite right-hand, but these are right-hand rectangles I've drawn here. So when k equals 1, I have the right-hand height. So I'll have the height at this point. So for every x value then, I'm going to go pi over 6 is the starting, plus for every k value, I'm going to move over 1 delta x. Okay, so then I can show that for this one here, for the starting value, we're going to use k equals 1, and that n is infinite if we are going to use an infinite n. Okay, and then this just works out to be pi over 6, which is my starting value. Okay, this just confirming that that's my start point. My expression for my end point, again, I'm going to start at pi over 6. I'm going to add pi times k over 3n. But my end point is going to be when k is the last term, which in this case, we're going to go to infinity when n is infinity. So this is 3 times infinity, like that. And since those are both linear terms, they cancel out. So I end up with pi plus 3 pi over, pi over 6 plus pi over 3, which gets me to the n value, which is pi over 2. Okay, so I'm just confirming that I have the right end, start and end bounds. I have the right expression for x. So now I can put this into my sigma notation. So I'm going to write like this. The exact area from 0, it's not 0, from pi over 3 to pi over 6 to pi over 2 of sine x that exact area can be done with a Riemann sum limit as n goes to infinity of the expression sine, I need to sum my sum from n equals k equals 1 to k equals n of sine of x. My x expression is going to be pi over 6 plus 3 pi k over 3n. That represents my x expression, and I also need a delta x in there, which is pi over 3n, and that represents my delta x. If I sum up each of those rectangles, I'm going to get the Riemann sum. If I let the n go to infinity, I will have the exact area, which is going from my sigma to my integral. So this process is very similar to the definition of the derivative or the Newton quotient, where we let the limit go to of h go to 0. This is very similar. We're just using infinitely small thin rectangles to get an exact area to go from the Riemann sum to the integral.